her to calculate.
Okay. All right, first thing we're going to do is review a little bit of ionic bonding. So you don't need to write this part down, but you need to pay attention and you need to be like, yes, this makes sense, or whoa, I don't get it. I need to go back and study some. Okay, that's a little mental check. Hey, or I need to study some. I need to come in and ask Ms. Anderson some questions before or after school, because if I don't get ionic, she's not teaching it again. She taught us for 4 days already. I need to put some time in. Okay, so kind of do a little mental check. How are we doing? How do I know what I'm doing? All right, in ionic bonding, electrons are lost or gained, the resulting formation of ions in ionic compounds. Are you good with the fact that ionic bonding is about losing and gaining electrons? Yeah. Remember that yellow sheet? We drew the arrows from where the metal started with them and they went to the non-metal. We good? Ionic bonding was between the left-hand side, the metal, and the non-metal on the right-hand side. We're good with that? Okay. And then those ions formed. What is an ion?
Charge.
A charged particle, a charged atom, right? And it's charged because the electrons, extra or shortage of electrons. It's all about those electrons that are gained or lost. So if we start with potassium, potassium is in group 1A, so it has 1 valence electron. Fluorine is in group 7A, so it has 7 valence electron. What is potassium going to want to do? Potassium's going to want to lose 1. Fluorine's going to want to gain 1 or take it. So potassium's going to give it to fluorine. Fluorine's going to take it, and it's going to move over. Fluorine is now happy and stable. Potassium is now happy and stable. Yeah. So potassium gets a positive charge. We would call that positive charge a cation. Yeah, cats. Cats are positive? I don't know. Cations are positive though. The negative one is the anion. Okay. So the compound potassium fluoride, IDE ending, consists of potassium ions and fluoride ions. Okay. We good with that? All right. The ionic bond is the attraction between the positive and the negative. Opposites attract. So when you have a positive ion and a negative ion, those two are going to attract together. That's what holds that bond together. Are we good with that? All right. So, new stuff then. Covalent bonds are going to be different. Covalent bonds do not give electrons from one to another. Covalent bonds are not between metals and nonmetals. Covalent bonds do not involve cations or anions. So basically, ionic bonds is one thing. Covalent bonds is a completely separate area that we're looking at. Okay, it's different atoms that are involved. It is a different way of bonding. It's a different way of naming them. We don't worry about charges because covalent bonds is not about ions at all. In a way, covalent is easier. It has one little thing that you're going to have to memorize that goes along with it, but the rest of it, I think it's easier overall. But you'll have to take a look. You can tell me afterwards, okay? Especially after you've done ionic. Covalent seems to be a little bit easier to handle. But you can tell me afterwards. We'll see what you think and what we need to do to make sure you're good with it. Are we all ready? You excited? Yes. Awesome. I can hear it in your voice. You're like, bring it. I feel like I should be a cheerleader. I would fail miserably. All right, so what are covalent bonds? In covalent bonding, atoms are still trying to get to be like your noble gases. They are still trying to become that full valence level, just like any of the noble gases. We usually call it the octet rule because we think of that 8 valence electrons. Which noble gas is the only one that does not have 8 valence electrons?
Helium.
Helium. Why is helium still stable?
It's a noble gas.
It's a noble gas. The first shell only has 2 electrons, and helium fills up that first shell. So it's not that it has 8, it's the fact that helium's shell is full. So our octet rule is just having that full valence level, whether it's the first level, the second level, the third level. So again, covalent bondings, they still want to become like the noble gases. They're still trying to get that full valence level. Instead of gaining or losing the electrons though, covalent bonds are going to share the electrons. Both atoms will think that they're using or having those electrons. It's like little kids that finally learn how to share. They're both happy. They both get to play with the toy. George right now doesn't understand that. So if he has that pair of socks, he doesn't want you to have the pair of socks. Only he gets the pair of socks. That's more like the ionic bonds. He gives if he wants to, very rarely. Mostly he takes. He's kind of like a non-metal. He just takes those electrons. Someday he will learn how to share. Then he will be more like the covalent bond, where we're all happy. When mom has a popsicle, George can have a popsicle, but we can share. It's good.
I love how you're comparing like fun to like.
Why not?
No, it like makes sense though.
Yeah. So
Teaching
covalent
this at
bonding.
an early age.
Covalent bonding is all about sharing. They both get to use the electrons. They both feel like they have full shells at different times, and it makes them both stable. The shared pair is called a bonding pair. Different atoms will have different numbers of bonding pairs. You can either have a single bonding pair, a double bonding pair, or a triple bonding pair. Single, double, or triple bond. There's no quadruple bond that we're going to worry about at all. I've never seen one. I don't think one exists, but I won't completely rule it out. So shared pair electrons, your bonding pairs, single, double, and triple bonds are available. Which one do you think is strongest? Single, a double, or a triple bond? A triple bond, yeah. Think of having 3 ropes, 3 things connected. This would have 3 very strong bonds. Harder to break 3. Are we good? We're going to go through some examples then. Chlorine. Chlorine is one of the atoms that will actually bond with itself. There are only a few. There's 7 atoms that will bond with themselves. Chlorine is one of them. So we're going to go through chlorine's example of bonding and kind of take a look at what it does in order to share those electrons. How many valence electrons does each chlorine atom have? 7. Yeah, it's in that halogen group, remember? So chlorine, each of them would have 7. So if we draw our valence electrons, we'd have 7 valence electrons on each of the chlorines. And if we look at how they're going to react, each of them has one open spot, right? Of our Lewis dot structure. Each of them has that one open spot. If we take our chlorine and kind of figure out what it wants to do, each of them wants to gain an electron in order to get up to that octet. Would they want to lose 7 electrons? No, that's going to be way too much work, too much energy. So instead, they really want to gain one. Neither of them want to give up. They just both want to gain. It's going to take too much energy to break that. If we remember the electronegativity, upper right-hand corner is the greatest electronegativity, right? So chlorine's on that right-hand side. It's going to have a great deal of electronegativity. It's going to take too much energy to pull out an electron. So instead, they're going to try and share. They're going to try and both use those electrons to give themselves the octet. So if we watch chlorine, I'm going to leave the right one in place, and I'm just going to fiddle with the left one and kind of move it in a way that's going to get it to work. Is that kind of cool? Kind of fits together. In the very center there, I just flipped my Cl upside down. In the very center there, we have the shared pair of electrons. One belongs to the right-hand chlorine, one belongs to the left-hand chlorine. They both think they're using it. So my right-hand chlorine thinks it has 8 here. My left-hand chlorine thinks that it has 8, making it an octet also. They can only have 8 as long as the other chlorine is there, because in the center they have their shared pair of electrons. They have to have that shared pair. They both have to use that middle set. So what happens is that pair of electrons, remember those electrons are set up in energy clouds or regions by the electron cloud model. So those electrons are floating around both chlorine atoms. So sometimes the right-hand chlorine atom has them. It thinks it's full. At other times, the left-hand chlorine atom has it as they're moving around. So it thinks it's full. Neither of them have 8 electrons the entire time. But the way those atoms or those electrons are moving around, it's with each atom long enough that they think that they're stable. They have the illusion of being stable because of how those electrons are moving back and forth. So we would call that a bonding pair. That would be what we would call a single covalent bond. Single covalent bond. Because there's just one pair of shared electrons. So this would be our Lewis dot model. If I asked you to draw your Lewis dot model, you could draw something like this, or our sharing of the pairs of electrons. We're going to show you another model today. It's called the structural model. So if you can just make a note of the structural model. Structural model. The structural model replaces any pair of electrons with a structural bond. It's just a line that represents the bond that's shared. So when we use the structural model, we just take our pair of electrons and put a little dash there. So you still have your valence electrons around the rest of the chlorine. You still have the 6. And then the last 2 are represented just by that dash, the bond between. Because there's only one pair of electrons that is shared, there's only one dash. If we had 2 pairs of electrons that are shared, how many dashes? 2. There's 3 pairs of electrons that are shared, 3 dashes. So any time that you have a pair of electrons that are shared, you would have a dash that would represent that shared pair. A dash that would represent your single covalent bond or your covalent bond. Is this making sense so far? Doing okay? So we have to get to having that octet, and it's just finding an arrangement for our atoms that puts it together. What would be our formula for Cl and Cl? Cl2. Okay. So chlorine molecule is just Cl2. You will have times where you've got different types of materials together, so it's not just an atom bonding with itself. There are just a few atoms that bond with themselves. Otherwise, they're all going to bond with different atoms. Oxygen is another diatomic molecule. It will also bond with itself, so it has O2. So if we go with the O2, I just moved my valence around so it'd be easier to show how they shared. Oxygen and oxygen both have 6 valence electrons. They both, again, want to gain 2. They've got 2 unpaired electrons. So if you put those together, they're going to try and share those 2 pair, because they're going to try and fill up. If there's nothing else to bond with, they're going to try and fill up those 2 pair with itself. So both of them are going to try and gain the 2 electrons. They're going to share the 2 electrons. And if they share both pairs, individually they've got 4 electrons on their own, 2, 4, and then 6 would be a shared pair, and 8 would be a shared pair for those last matching up. So 6 valence electrons on its own, and then 2 that are shared for each molecule of oxygen. Gives each atom of oxygen a full octet. They think that they're stable. They act stable, they interact with anything else, stable. And each one is happy. They're in a good spot. So if I look in the center then, I've got a shared pair on top, I've got another shared pair on the bottom, so I have two pairs of shared electrons. If I wanted to draw the structural diagram, what would it look like? Kind of look like an equal sign, two dashes, and then I'd have my 4 valence electrons on the outer 2 oxygens. So this would be a double bond, and it would look like that.
Boom.
So covalent bonds will only form between 2 nonmetals. Covalent bonds will only form between 2 nonmetals. Where do we find the nonmetals? In the upper right-hand corner of the periodic table, plus hydrogen. So upper right-hand side of the periodic table plus hydrogen. Those are the only ones that are affected by covalent bonds. The rest of it, if it has a metal and a nonmetal, is going to be ionic bonds. If it has 2 metals, that's something else. We'll talk about that later. The 4, yep. Just to get it moved over so you can see the shared pair. So as we're moving the Lewis dots, once you get the Lewis dots set, you can move how those electrons are shown, so you can try and get them, so you can rotate them, you can do things. When you're on paper, it's harder to rotate, so I tried to show you something you can do on your paper to easily show what's going on with the electrons. So instead of having them spread out on either side, and rotating them in, I just put them 2 pairs there, so you can easily see how they're matching up. So we have our pair that's shared. Again, 2 nonmetals that are coming together, whether it's chlorine, whether it's oxygen, whether it's bromine, whether it's hydrogen, it has to be 2 nonmetals. And then those electrons are going to be shared. Again, molecules are going to be stronger the more bonds you have. So if you have a double bond, it's going to be stronger than a single bond. A triple bond will be double than a will be stronger than a double and a single bond. So you need more energy to break apart those bonds if you want it to break them down. You've worked with or heard some names for covalent bonds before. Carbon dioxide. What's the formula for carbon dioxide? CO2. Carbon is a nonmetal. Oxygen? Nonmetal. So that would be a covalent bond. Carbon dioxide. And you knew that the di meant 2. Okay, how about carbon monoxide? What's the formula? Just C and O. Again, covalent bonds. How did you know that the formula was different from carbon dioxide? Di and mon. Okay. When we're doing covalent bonding, the way we know what the formula is, instead of having to look at charges, we look at what are called prefixes. Prefixes have the mono, the di, the tri, tetra. Those prefixes tell you what your formula is, rather than you having to do balanced charges. You can just go by what the formula says. So it makes it really nice as long as you know your prefixes. So for covalent compounds, we will only need to know up to 10 for your prefixes, but you will need to memorize these. So this is the one thing you have to memorize for your covalent stuff. Once you have these memorized, it makes naming and writing the formula very easy. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 penta, 6 hexa, 7 is hepta, 8 octa, 9 is nona, and 10 is deca. Some of these will be familiar to you already, I'm sure. Others you probably haven't used as often, or if at all. And so it's really going to take you some time just to make sure that you practice these and learn them and know them. Now, the second element, the anion, when we wrote it for ionic bonding, what was the ending that we put with it? Ide. Ide still happens here. So when you look at carbon monoxide, carbon tetrafluoride, I can't think of them, sulfur dioxide, all of them end in IDE. When you go through, you still change that second element to an IDE ending. So that stays the same. Let's have you go through and practice a naming one. Let's do S7Cl2. S7Cl2. Write down the name for me. S7Cl2. 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 What would S7 be? Heptasulfur and Cl2. What would Cl2 be? Dichloride. Ide. So heptasulfur dichloride.
That's one word.
2 words. Heptasulfur dichloride. What if I told you about a super dangerous molecule, dihydrogen monoxide? Dihydrogen monoxide. It's very toxic. Dihydrogen monoxide. You don't want to, touch this stuff, breathe this stuff, it's terrible.
H2O.
Very good. Have you ever heard of water referred to as dihydrogen monoxide? That's the formula name. Dihydrogen monoxide is water. But most of the time we just refer to it as water because who wants to go walking around saying, hey, you want a glass of dihydrogen monoxide?
I would.
I'm thirsty. Can I
What
have
is
some, waitress, I need some dihydrogen monoxide, please, with ice. Right
People
here.
would think it's poison. It'd be hilarious.
On the rocks. On the rocks. Okay, so ammonia is another one. Ammonium is one of your polyatomic ions. You've heard of ammonium before, right? It's just NH4. It has a set formula. So water, we know H2O. It's a covalent bond. Hydrogen is a nonmetal. Oxygen is a nonmetal. So 2 nonmetals together form a covalent bond. They share their electrons. Hydrogens fit in right where the 2 openings that oxygen has. Oxygen has its 6 valence electron, missing one on this side, missing one down here. Hydrogen fits in. Hydrogen shares. Hydrogen thinks that it's full with 2, right? Because how many shells does hydrogen have? Just the one shell. The first shell holds 2 electrons. So each hydrogen is full, and then oxygen thinks it has 8 because it's sharing with hydrogen, right? Does that make sense? All right. Okay, last bit then. H2O2 would be dihydrogen. Oops.
I got excited.
H2O2 would be dihydrogen dioxide. The last trick with naming, if you have like carbon dioxide, CO2, if there's only one of the element in the front, you don't have to do mono carbon dioxide. If you just say carbon, it's implied that it is one, unless you put dicarbon in front of it. So if you only have one for the first element, you can skip the mono. You don't need that.
Are we getting homework today?
Yeah.
Hey,
We're going to a lot.
So what kind of
All right, so last little bit then is the diatomic molecules. Diatomic molecules are the atoms that bond and combine with themselves. So we said that oxygen will combine with itself, chlorine will combine with itself. Only 7, the special 7 I call them. Special 7 will combine with themselves. The rest of the atoms will not combine with themselves to create stability. These 7, when they bind with themselves, they're stable. They're happy, they're in a good spot, they don't need to look for reactions with other things. They still will react with other things, but they're stable on their own. Those 7 are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Again, they are the only 7 that will form stable molecules when they combine with themselves.
Will atoms combined get closer towards the same atom?
Say that again.
Will like 2 atoms combine to get closer to a single atom?
They will find something else to bind with. So if you've got just carbon, it's not going to combine with another carbon unless there's something else that it could bind with too. So it's not, carbon and carbon won't go together just because they're looking to find more stable, astable way to bind. So you need some carbon, you need some hydrogen in there, or some oxygen or something else. Once you get this slide down, if you can pull out your periodic table, the colored one that has all your info on it, we're going to add our last bit about diatomic molecules on there. Yep, that one. Not the one from yesterday. The big one has all the info, masses, atomic number, valence electron, 2A, this one right here. Is everyone good? If you go to the upper right-hand corner of each of the diatomics, we're going to have you put a star in the upper right-hand corner of each of them. So hydrogen, and then nitrogen, oxygen, and fluorine, chlorine, bromine, and iodine. If you look at the shape that they form, and I put it on the board for you, it kind of looks like a 7 plus hydrogen. 3 across the top, 3 down, and then hydrogen.
Okay, what if you can't see the stars anymore?
You could use a permanent marker when you get home tonight. Or you could put a star next to them or something. So those are the 7 that will bond with themselves. That's going to be more important once we get into our chemical reactions next unit when we're actually writing formulas for reactions. Right now, just so you know that they react with themselves, that's all you need to know. But you've seen like H2 just show up before, or Cl2 just show up in a formula before. This is why. So when we start writing formulas, instead of having magnesium plus oxygen just as Mg plus O, it would be Mg plus O2. Oxygen would not show up just as a single atom in oxygen. It would always show up as a pair bonded together. We'll talk about that more. Right now, just know that these will always bond with each other if there's nothing else for it to bond with. All right, so today we're going to focus and practice on some of the covalent bonding things.